Are you ready to unravel the secrets of the universe? Have you ever wondered how gravity works on a cosmic scale? How massive objects like planets, stars, and even black holes bend and shape the fabric of space-time around them? What if I told you that there is a set of equations formulated by none other than the genius Albert Einstein that describe the very nature of gravity? Well, in this video, we are going to delve into the complex interplay between matter, energy, and space-time geometry. We are going to explore and understand each and every component of Einstein field equations, which is the key to unravel the mysteries of the universe. Although these equations are very complex equations, I'm going to show you with a lot of illustrations and keep the mathematics at its minimal. So whether you're a scientist, you're a science enthusiast, a curious mind, or simply someone eager to expand your knowledge, this video is for you. Get ready to have your mind stretched as we unravel the beauty and complexity of the Einstein field equations. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to a beginner's guide to Einstein field equations. First, let us look into what are the topics that we are covering today. So we are going to cover what are Einstein field equations, what is the meaning of the equation, what are the different components of the Einstein field equation, what is symmetric tensor and how significant it is in terms of general relativity, what is the Ricci curvature tensor, the Ricci curvature, the Riemannian manifold and the Riemann curvature tensor, what is the relationship between them, Ricci curvature and the measurement of geodesics, what is a metric tensor, why do we need and what is the significance of metric tensor, the rubber sheet analogy, the Riemann curvature tensor, what are the components of Riemann curvature tensor, parallel transport and stress energy momentum tensor. I'm going to keep the mathematics along with that, but I will try to show you lot of illustrations so that the very concept of all these complex things become very easy. So this is a good time to start. So first we are going to understand what are actually Einstein's field equations. Now as you see that I have already mentioned this in plural, that is Einstein field equations, although some literature say that it is equation. That means you have already understood that it is a set of one or more field equations. What are those? Let us look into this part of our video. So first we will look into the gross understanding of the Einstein field equations. The left hand side of the equation tells that measures the curvature of space-time. The curvature of space-time is basically denotes the geometry of space-time. If I take the right hand side, it measures what is called the matter energy content of space-time. Matter energy means how much matter is measured, how much matter is present, and this actually registers what is called the matter movement. So you already understand, if there is a matter only, then there is a geometry of space-time, that is a curvature, and this curvature is measured by some amount of mathematics, and these are equated by this equal to sign. So as the famous scientists have told, that space-time tells matter how to move and matter tells space-time how to curve. Now this is all in all, just in a nutshell, what this Einstein field equations is all about. This is just a simple understanding. The left hand side measures the curvature, the right hand side tells the matter movement. But our entire video is concentrated in understanding and further understanding the points and subpoints and further concepts of this particular equation, which is right there on the top of your screen. Now see, if I look into this point of an equation, first I would like to show you what are the constants, because constants and variable only make out the equation. So first is the lambda, which is called the capital lambda, which is a cosmological constant. This c4 is called the speed of light. Don't ask me why it is c to the power 4. I will explain it in a next video because it will require something which is called a dimensional analysis. 8 pi is basically the constant. G is the good old Newton's gravitational constant. So all these are basically constants. So these are the constants which will always remain constant in the equation, and now it is this time, let us look what are the variables in the next part of our video. So first we will look about this R. Now you might find as a repetition, because those who have watched my earlier video on tensor, just hold on, because this video is going to be much more deep details containing lot of mathematical understanding. So Ricci curvature tensor, actually it measures how the volume of matter changes when it moves through flat space to curved space. We will look into this. This R is basically called the Ricci scalar, which keeps the track how the size of a ball deviates from Euclidean space. Right at this moment, if you don't understand what is Euclidean space or why I am talking of the size of a ball deviating, just hold on, everything will be clear by the end of this video. Then comes this small g, which is very important. We are going to look into it. This is called the metric tensor, which measures the distance, or you can say the causal structure of space-time. Next comes this Riemann curvature tensor, which is a useful tool for measuring curvature on Riemannian manifolds. We are going to look into it. But as you can see in the entire field equation, it is not written. Why? Because this is hidden. Why it is hidden, we will soon reveal in the next part of our video. Then comes the T, which is called the stress energy momentum tensor. We have already encountered just now, which calls the matter movement through the space-time. So 1, 2, 3, 4, 5. These are the components, and this is a very gross basic understanding what those components actually means. Ricci curvature, Ricci scalar, metric, Riemann, and stress energy momentum tensor. So some of them measures curvature, some of them measures matter movement. How they measure, what do they measure, coming up in the next part of our video. So if we take the Einstein field equations again, we see that there is something which is called a mu nu, which are the Greek alphabets. So what are that? These are dimensions of space-time. What are the dimensions of space-time? Simple. We have considered time, x, y, and z. So there are 4 dimensions of space and time. Again, if we take the g mu nu, it is also a dimension of space-time. Again, it is the same. If we take another g mu nu, again it will be the same, and another t mu nu, again it will be the same. Now you might be thinking, what is happening out there? Why I am showing all these 4? I am showing all these 4 just to tell you that these are actually mu nu are actually indices. That means in which direction of space and time you're taking, and this 4 plus 4 plus 4 plus 4 makes up 16 equations. That means what you are looking right now on your computer, on your mobile or tablet, is a set of 16 partial non-linear differential equations, which almost took 10 plus years for Einstein and other brilliant mathematicians and physicists to frame. And we are looking at right at this moment. But soon we will look that these 16 equations are not 16 equations, but they are reduced for our convenience. What are those reduction and why it is done, coming up in the next part of our video. So first you see, if you don't understand, don't worry, I will be explaining it what it is. This is called the metric tensor. You can just call it as a 4 by 4, a kind of a metric, 4 by 4 matrix. It is a tensor or whatever you like it. Now you see, this metric tensor, actually what they do is that they measure the causal structure of space-time. Now out of those 4 plus 4 plus 4, 16 components, I've just told that 6 of them cancels out. Why? Because they are a duplicate. I won't say duplicate, but they are, I would say, isometric or isomorphic to each other. So they can cancel out and we get only 10 set of equations. What are those? G01 and G10, they cancel out. G02 and 20, they again cancel out. G03 and 30 again cancels out. G12 and 21 again cancels out. And G13 and 31 again cancels out. So you see 1, 2, 3, 4, 5 of them is getting cancelled out, and the 6th one is this G23 and G32. So what I'm trying to now, why it is getting cancelled out is a different part of the story, but you can see 10 is similar to 01. Obviously 20 will be similar to 02. So these components gets cancelled out, and what we get is this 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So this G mu nu is actually a set of 10 partial nonlinear differential equations. Now again, if we take a different kind of a coordinate, we can further reduce this 10, but that would take a lot of mathematics. I'm not going into it. So finally, what do we understand? What we understand is that this is a symmetric tensor. That means G mu nu will be equal to G nu mu. So the indices, even if they swap, it hardly matters. And what does that mean? In general relativity, what the metric tensor is the fundamental object. So it actually captures what we call in Cartesian coordinate time, distance, volume, curvature, angle, and the future and the past. So the entire causal structure of space-time, which includes the time, the distance, the volume, the angle, the future, the past, everything is being captured in this 4 by 4 matrix that is called the metric tensor. And this is symmetric. Symmetric means if you swap around the indices, it hardly matters. And what does that mean? If that, say for example, this on the right hand side, as you see that this is a curvilinear coordinate, and I take these red dots, for example points. So from here to here, here to here, here to here, and here to here, these blue lines, actually you can understand that actually these are time, distance, volume, etc. Although they are not so, this is just a schematic diagram to make you understand. So this is the measurement. This is the function of the metric tensor. We will deal metric tensors separately in this video, don't worry. But this is actually symmetric. Now you might ask a question, so what does symmetric tensor at all means, and how does it makes a difference? That is coming at in this part of our video. What does it mean as tensor to be symmetric, and why it is important to general relativity? I have taken first the mathematical definition. A symmetric tensor is a tensor that is invariant under a permutation. That means whatever things that I change, it will be the same. Now you see you're already getting a catch. That is, if the things are invariant, Einstein wanted a kind of a covariant theory of gravity where whatever the frames of reference and whatever inertial or non-inertial frames we are measuring, the laws of nature or the laws of physics would be invariant. So you get for every permutation sigma of the symbols 1, 2, 3 and so on, right? So you see that Tij and TGI are similar. This is called rank 2 contravariant tensor. Don't worry. If you don't understand contravariant tensor, you can go to my video on tensor. You will see there are two types of tensor, contra and covariant. That is not an issue. Also, Tij equals to T sub Gi. This is called rank 2 covariant tensor. Don't worry about this. These are just mathematical I would say implications which if you can just ignore for the right way. And that is why G mu nu equals to G nu mu, symmetric nature of the metric tensor. So what does it tell? That if mu nu and nu mu are being swapped at each other, the laws of physics will be invariant whatever value they take. Isn't it? So the laws of physics will always be the same, and that is really the motto of GR, general relativity. And here comes Einstein's famous line: the general laws of nature must be expressed by identical equations relative to all other systems, whichever way they are moving. Right? So now you got our entire understanding that why symmetric nature, why metric tensor is symmetric, and why symmetric tensor, in spite of swiping the indices, really doesn't make any sense. Why? Because the laws of nature will always be the same, and that is the basic idea of our physical model. So what do you see from here is that the symmetry of the metric tensor is important. Why? Because it allows us to define the notion of distance in curved spacetime. Now you might have a question, so what? We have Pythagoras, we have Euclid, we can measure the distance of spacetime in a flat space. So how does it matter that we have to take a symmetric tensor? Certainly not. Let me show you an example. If this is a flat space and these are the two yellow dots, I mean to say for example points, and if I draw a straight line, then what I can do is that I can simply calculate d equals to x2 minus x1 whole square plus y2 minus y1 whole square. But this is not so here. On the right hand side, this wiggling blue curve. And if this is a curve, then I have to take 2 points, and you see how the line goes here and here. That means the distance between 2 points is not necessarily the length of a straight line, and that is why we cannot use Pythagoras and Euclid. I hope this is clear, right? So because from flat space we are moving into curved space, and we cannot use the general Cartesian coordinates, we need to do something new which is called a geodesic. I will be explaining geodesic in a separate video because that requires a lot of geodesic equations, but this is what is called the geodesic. Geodesic means the shortest path between 2 points. And you see this geodesic is measured by whom? This metric tensor. So if I am not using a Cartesian coordinate, if I am not using a flat space, then I need a kind of a metric which will measure the distance between two lines which are not specifically straight line. They are geodesics. That means the shortest path between 2 points. And obviously that should be smooth and that should be curved. And that is why if I swap between the indices, because in the curved space everything changes at every point of time, I can measure all the laws of physics invariant. That means there are no changes. I hope this part is clear. Now let us proceed to the next part. So in a flat space, you see what we get is called an identity matrix. I hope this is clear from class 6-7. Identity matrix is something which will have a diagonal element all 1 and will have 0. So this is an identity matrix. But if we plot the same matrix in spherical coordinates, I'm plotting the same matrix in spherical coordinate, you see what happens. 1 minus 1 r cube r squared sine square theta. Obviously this would be true, because in spherical coordinates identity matrix doesn't work. So the basic point that I'm trying to make is that in flat space, if I'm using an identity matrix and I'm moving from identity matrix to make another identity matrix in a spherical or a curved coordinate, it won't work out. That means if I want to plot the same tensor, or what we got in the earlier part, this one, this tensor in this part of the video, that is the spherical coordinates, it won't hardly work out. The reason is that this is not an identity matrix. And G mu nu and G nu mu, the symmetry of the metric tension ensures that geodesics are always smooth curves. So the symmetry, what will it ensure? It will ensure the geodesics are always smooth curves. That means there is no bump, there is no jump, what we call as a smooth manifold, a similar definition in calculus. It is always smooth. So if flat space does not have an identity matrix, the spherical coordinates or any polar coordinates would not have an identity matrix. So there is no point in plotting the identity matrix. But there is a point in putting up a symmetric tensor, because we need it as a smooth curve and geodesics are smooth curves. So finally, what do we learn from here? Let us summarize in simple language. We learned that symmetry of the metric tensors allows us to define the notion of a distance in curve space. We also understood that symmetric ensures that geodesics are always smooth. That means the measurement will be easy. The symmetric of the metric tensor ensures that Einstein field equations are consistent with the general principle of covariance. That means I would later explain what is the covariant theory of gravity, something which is in hand in hand going with another. That is called that is what is called the field equation. That is, the symmetry of the metric tensor ensures that. And it also means obviously the laws of physics will be same in all frames of reference, and the symmetry of the metric tensor allows us to define the notion of distance in curved space-time, and it ensures that the field equations are consistent, and it is in principle of the general covariance. So we have heard about symmetry, symmetric metric tensor, symmetric property of this tensor. What does that mean? This means actually this, that the symmetry will ensure that the laws of physics are consistent in all frames of reference. The question is that, is metric tensor the only tensor which is symmetric? Certainly not. Let us look. This is stress energy momentum tensor, and here also if you plot, you will see it is a symmetric tensor. T mu nu will be equal to T nu mu, and this is a symmetric tensor, and more or less you can now imagine that this will also be in accordance with the general covariance, this, that, and all the laws of physics will be the same. So whatever is there in the metric tensor, that stress energy momentum tensor, the symmetric nature of the metric tensor will guide the general principles of the laws of physics. First we come to the first most important component, which is called the Ricci curvature tensor. Now we have to go back to Italy now and meet this wonderful person, Gregorio Ricci Curbastro, an Italian mathematician, and is almost famous for the famous tensor calculus, and he was the former student of this person, Tullio Levi-Civita, and he wrote the famous single publication, which is this one, and I won't dare to pronounce it. It is in Italian. It means Lecture on the Theory of Surfaces, a pioneering work on the calculus of tensors, and he signed it as Gregorio Ricci. So this is kind of a, I would say, evolution of how the tensor calculus were formed with Gregorio Ricci and Tullio Levi-Civita. So we go ahead and first understand what is a Ricci curvature tensor. First we will look into the simple definition. So Ricci curvature tensor is a geometric object, and it can be considered as a measure of the degree to which the geometry of a given metric tensor differs from the local ordinary Euclidean or pseudo-Euclidean space. That means you can understand there is some kind of an aberration, some kind of a disturbance which will occur when we move from Euclidean to non-Euclidean space, and Ricci curvature tensor is going to register that anomaly. How a shape is deformed as one moves from the geodesics once in the space, and in general relativity it tells that how a volume between geodesics change due to curvature. Okay. So we have understood that there will be an anomaly, there will be certain change, there will be change in terms of shape or anything or volume when we are moving an object from a Euclidean space to a non-Euclidean space. Now you see how it is interlinked. Ricci curvature tensor gives rises to Riemannian manifold, which gives rises to Riemann curvature tensor. Now what does Ricci curvature tensor do? Ricci curvature tensor measures the curvature that is present in manifold. And what does Riemannian manifold do? It actually is a contraction of the Riemann curvature tensor. I will soon show you how the contraction happens. It is very simple. And this Ricci curvature it acts on the manifold, or you can call it as a surface. And what is the surface does? This surface, Ricci tensor, is a contraction of the Riemann curvature tensor. And what is a Riemannian manifold? It is a smooth manifold, as simple as a manifold. That is a notion of angle, length, etc. And this Riemann curvature tensor goes back to Riemann manifold. And what does it does? It measures the manifold's curvature. So you see, Ricci curvature tensor is actually measuring the curvature present in manifold. Where this curvature is present? It is present in the Riemannian manifold. And because this Ricci tensor is a contraction of Riemannian curvature tensor, so in one way you can say Ricci and Riemann are related to each other, obviously. So Ricci measures the Riemann manifold, and the Riemann manifold curvature tensor actually goes back to the Riemannian manifold and it measures the manifold's curvature, and that also again goes back to the Ricci curvature tensor, which is just a contraction of the Riemannian manifold. This is how these things are related. So the Ricci curvature tensor measures how a shape is deformed as it moves along the geodesics in the space. Let us see an illustration now. These are the two curved coordinates x and y, and this is the curvilinear point graph, and this is the point, and here it moves slowly. You see it goes here and down, and it ends up here. I take another point and I again start moving from here. It goes and here you see what is happening. What is happening is that the two initial parallel geodesics, typically in a flat space-time, it should have gone parallel and parallel and parallel till infinity, is now trying to deviate. And this deviation is being measured by what is called Ricci curvature tensor. So what it does is that Ricci curvature actually measures how much the space-time and the volume change in direction. And you see this R mu nu describes how much space-time volume between these geodesics change in each direction, and the geodesics began to deviate from each other. So how much will be the change? As I told, there will be an anomaly, there will be an aberration, and that is from flat space-time, how it moves to a curved space-time, and how much the volume is changing, that is what R mu nu is going to register. I hope this is clear. Let me give you a further example. This is a globe, and these people are trying to move, the purple and the green, and you see they meet at the poles. And here is the two straight lines, and if I take a ball starting right from the south pole and I try to move the ball to the north pole, here it goes, here it goes, here it goes, and here it goes. So what happens is that the size of the ball shrinks. The size of the ball shrinks. That means it is a positive curvature. This R mu nu registers that. If I show a further illustration, this is the one. Don't worry about S vec. This is basically what is called a sectional curvature. We are not dealing with this. And here you see again they converge. It is greater than 0, and it diverges, which is less than 0. This is actually the measurement that if I start moving in a curved space-time, how the geodesics or the shortest path will look like. So here is a ball. And if I'm moving in a straight Euclidean space, here it goes. Nothing changes really. Ricci curvature equals to 0. The size of the ball remains the same. Here is something which is converging. So if I take the ball, it shrinks further. Ricci curvature is greater than 0. The size of the ball shrinks. And if I take a geodesics who are diverging, I take a ball, it increases, and increases. And Ricci curvature is less than 0 because the size of the ball increases. Quite clear, I hope so. So what can we finally summarize from here? That Ricci curvature is a geometric object which measures the curvature of manifold. It is developed by Gregorio Ricci Curbastro, and Ricci curvature tensor can be thought as a measure of how much a shape is deformed. Obviously, when the sizes are increasing, the shape will deform. And geodesics are the shortest possible paths. The Ricci curvature tensor can be measured, used to measure the curvature of variety of spaces, and is a very compact presentation, because otherwise the equation would look too long. Some of the important information provided by the Riemann curvature tensor. So this is in summary what is the Ricci curvature tensor, which is actually measuring how we are moving and how much the volume or the shapes are changing and how much is the deviation from a Euclidean path to a non-Euclidean or curved space. Time now to look into the next part, which is called the metric tensor. Now I'm going to give you a very easy, I would say, easy way out and an easy understanding by using an analogy of a currency. But before that, I would like to tell you what a metric tensor looks like. You have already looked into this. So it is basically a fundamental object of study. Obviously, it captures all the geometric causal structure of space-time. It is used to define notions, and it measures distance, volume, curvature, and metric tensor plays the role of the gravitational potential in GR. Yes, metric tensor, or the normal Newtonian or Poisson's equation of gravitational potential, is being replaced by metric tensor. Now I would like to show you an analogy. Say for example, Indian currency is compared to US dollar. So currently it is 82 rupees 82 paisa, something like that. If I convert it with Japanese yen, yen versus dollar, it is 139.37 Japanese yen and 34.87 Thai baht. So what I'm trying to take a point is that each of these countries have each of their own metric, and that is why it is Indian rupee, Japanese yen, Thai baht, US dollar, etc., etc. But I'm taking dollar. Why? Because I'm making it as a benchmark so that everybody understands dollar, and if I say $5 to a Japanese yen, he or she can immediately convert it to the current currency and they can understand what $5 means to their context. That is what metric tensor does. In the curved space-time, this is a kind of a currency, is a kind of a yardstick through which the measurements of the curvature happens. So dollar versus INR, yen and baht, here also it will be the same. Let us look into this part of our video. So if I take that I am walking from here, I want to reach my home. I walk straight down. Right? So I have a kind of a metric, say G equals to D Euclid. I mean to say distance in terms of Euclidean path. Now I want to move from my home, from this place to my home, and I want to take a taxi. And this taxi is going to take a path around the pond. So here comes the taxi, here it meets. So here, if I do a metric, that is, I measure something, I get G equals to D underscore taxi. That means there are two metrics going to the same place. One is a straight one, which is directly reaching my home. One which is going the curved path through the pond, which is the metric of the taxi. So what do I mean by all this? What I'm trying to tell is that if I take the typical Pythagoras' theorem, then if I make the infinitesimal small distance, this would be ds squared equal to dx squared plus dy squared. It measures the differential distance. So if this is a curved space-time and these are the 2 points, here it goes and it measures the differential distance in terms of this. Don't worry what this ds squared, g11, etc. are. We will come later. But this is a kind of a quadratic equation. And this quadratic equation, the dx dy shows that things are not, or the measurements are not perpendicular to each other. Don't worry if you don't understand the equation, just understand that these are infinitesimal small distances between 2 points dx and dy, and these are not perpendicular to each other. And G, actually the metric, actually shows the amount of spread. Now you must be wondering, what do you mean by amount of spread? I'll just show you. If I take a graph like this and these are the lines, you see how dense these lines are compared to this, this and this. These are quite widespread out, isn't it? So much dense versus loose, and G, these things actually measures where you are. That depends upon the density of the curvature, whether it is dense here or it is loose out there. So this D actually is the metric tensor, which measures how much dense and how much loose it is. So taking an analogy, if I take this kind of a rubber sheet and if I draw a straight line, I can use the Pythagoras' theorem. And if I extend it further and I use this line and this line, then what happens is that the x side increases twice. So I use 2dx squared. If x and y, both of these increases, say for example this one, then I use this one, 2dx squared plus 2dy squared. Isn't it trivial? Now, if this is a kind of a stretched area, this is a stretched path, okay, and this is the curved line which is happening, and if I take this kind of a curvilinear coordinates and I plot these dots, then what happens is that if I take the same equation, this one and this one, then what I see, this dx and dy, as I told you, these are not perpendicular. That means if you remember that the unstretched matrix, you remember it is called the identity matrix. It is very similar, and we can use this one to measure the stretch matrix. But as you remember, this unstretched matrix is where in Euclidean space, but this is a stretched one. So this red line will be curved, and this G11G, this will actually measures where actually I am. So this is the understanding. This G11 or this G actually will measure how much amount the space is stretched. That is, it will contain what is called the stretching information. The stretching information will be covered in this G. That's it. I mean to say that would be a kind of an intuitive understanding. So from this, what we can get is this one, this metric tensor stores information, and in this curved path, whether I am going left, right, up, down, etc., how much and in which direction space and time is stretched, this will be measured. And we already know this is a rank 01, rank 02, 3, 4, etc., and this is what is called a rank 4 tensor. That means it is measuring space, time, everything in 4 dimensions. That is why it is a rank 4 tensor. And this is denoting what? Amount of matter which is stretched. Let me show you a similar analogy using mapping. So if I take this kind of a sphere, and this is the line which is moving, and this is the unstretched version, right? That means the identity matrix. And if I'm patching that unstretched path over here, over here, over here, so you get all those unstretched path, right? And these are the curved lines. That means if I put the stretched path, that means if I do the mathematics and understand the equation of this stretched path, which is this one, and if I put the unstretched equation or the dx dy on the stretched part, then I can obviously know calculate the g, and we can compute the distance between these 2 points using this kind of an equation. Let me go back to this for a while. So we know the unstretched equation through the normal Euclidean space, and if you put the unstretched patch onto the stretched global sphere, where it gets stretched, the layers get curved, and we can use this kind of an equation to find out that what are the distance between these points in the curved manifold and any kind of a causal structure of space-time. This is what is Ricci tensor all about, or Ricci curvature tensor is all about, which is measuring the, I would say the metric tensor is all about, which is measuring the causal structure of space-time, how much it is bent, how much it is stretched, how much it is going left or it is going right, whatever it is happening. So I have to first take the unstretched version, put it in the stretched version, and then I can get the expanded equation and I can measure it. This is what is called the basic idea of metric tensor, measuring the things in a curved manifold. Now we come to the Riemann curvature tensor, and we have to go to Germany now from Italy and meet this wonderful person, Georg Friedrich Bernhard Riemann, who made profound contributions to analysis, number theory, and differential geometry. In the field of Riemann analysis, he is mostly known for the first rigorous formulation of the integral, the Riemann integral, and his work on Fourier series and his contribution to complex analysis, and most notably the introduction of Riemann surfaces. He was a student of the famous prince of mathematics Carl Friedrich Gauss, and this was the seminal lecture which he gave in Göttingen in 1851, where all those Riemannian curvature tensor manifolds etc. were unrevealed, or I would say were put forward. Bernhard Riemann's On the Hypothesis which lie at the basis of geometry, very famous, and even after so many years it is still taught at college lectures and PhD level. With Carl Friedrich Gauss being his mentor, you can expect Riemann to do this kind of wonderful things. What are those things? What are those magical changes which Riemann brought in terms of differential geometry as well as with general relativity, coming up in the next part of our video. Oh wow, this is something really great, but don't worry, I'm going to break it down for you. This is what the Riemann curvature tensor actually looks like. So the Riemann curvature tensor is a mathematical object which measures the curvature of a Riemannian manifold. The question you have in your mind is, what is a Riemannian manifold? Don't worry, it is just a manifold. For the timing, let us understand to be a surface. It is a complex object but can be thought of measuring how much the manifold is curved at a given point. And here you see it has got 4 indices. That means it is taking 4 vectors and giving out a scalar. And it actually shows the 4 vectors that moves along the geodesic. Let us break down Riemann curvature tensor into certain simple components. This one represents the components of the Riemann curvature tensor. This one is actually the partial derivative with respect to coordinate. This part is what is called a Christoffel symbol, which I have already covered in another video. You can look into that, and represent the connection coefficients. What does this actually denote? This denotes that the Christoffel symbols are actually their derivatives. It involves taking derivatives of the Christoffel symbols and combining them in a specific way. Anyway, this is the Christoffel symbol. This is how it looks like. This actually measures a kind of a curvature in Riemannian manifold. We will look into it. Okay, so you see now this RAB, alpha, beta, whatever, this is more or less equal to this. Now this is actually the Ricci tensor, if you remember. That was mu nu, I have used it AB. Now this one, the 4 index, as you saw. See, this is called the Riemann curvature tensor. And as you saw, as I have told, that it was already hidden. So the Ricci curvature tensor is a contraction of the 1st and 3rd index of the Riemann tensor. And how is this one? This is the 1st index and this is the 3rd index. The question is that where it is there. So yeah, each of the component of the Ricci tensor is a sum of multiple components, and it shows over here. The question is that if that is so, then can we move along a curved surface keeping the vectors always parallel? For example, I want to take a vector and keeping it as parallel as possible, I want to move along a curved surface. Is it possible? This is what is called a parallel transport. I will just show you a very simple example. So if you really want to measure vectors, for example, I want to measure 2 vectors, which one is big, which one is small. So I can see here this is bigger and this is smaller, and this is smaller than this one. But what if you want to know that whether a space is curved or not? Now you might say that always I can look into the picture and say, but it is always not possible. It is always not possible to look at the picture and say, okay, this is curved. So what we do is that we take a kind of a way of comparing vectors at different positions in manifold. It is a way of transporting data along the surfaces. Now I say I take a plain Euclidean space, a triangle, which is kind of an equilateral triangle. This is my vector, and I have to move parallelly. I go here, I go here, I go here. I'm keeping it parallel. I became it parallel, and I came back here. So what does it imply? It implies that if I parallelly transport a vector along a surface, and if it comes back to the original point without any deviation, that means it has been successfully parallelly transported. And that means it is a flat space, it is not a curved space. So if a vector is parallelly transported and it comes back and exactly overlaps with the original vector, that means it has been successfully parallel transported and the space is flat. Now I will move along this globe. Here I am, and here I will moving. Here is my vector. I am parallelly transporting. I name the vector as V. Here I am moving. Here I am moving. You see this curvature. Now the vector is curving. Why it is curving? Here it goes. I move in here. I move in here. I am keeping it parallel. Okay. So the direction of the vector changes. Why? Now it is because due to the curvature. Now what will happen? Now I move parallelly here. Now I come to the North Pole. I move here. I move here. I move here. So what happens is that when I come back original, the blue one or the purple one is V prime. And you see there is a marked difference between the original yellow vector and the parallelly transported vector. Now you see it is not a successful parallel transport. Why? Because the vectors are not at the same place. And this is the difference. How much deviation? You saw earlier we talked Riemann curvature tensor which measure will how much the deviation has caused, and this is the deviation, V prime. So this one actually measures all the components of this vector in space-time direction. So you see that this is huge, monstrous Riemann curvature tensor. This actually measures this one. That means after coming back from the original place, how much deviation or how much change it has happened, and that actually measures the curvature, and that is measured by Riemann curvature tensor. So actually Riemann curvature tensor gives a complete description of tidal forces of general relativity. I hope this part is clear. So it is actually measuring a curvature, but when we parallelly transport and come back, it measures the deflection, that is the amount. So what we can say is that it is a measure of a curvature of Riemannian manifold. Obviously it is a tensor, so it takes multiple vectors 4 and gives back to a scalar because it has got 4 indices, right? It has a symmetric tensor, again because the orders doesn't matter. Riemann curvature tensors components that represents the amount and type of direction, and in general relativity it is used to describe the gravitational field, and in cosmology the Riemann curvature tensor is used to study the evolution of the universe and the gravitational field of a curvature of space-time. Now this is my another video, lesson number 11, where this Riemannian curvature tensor, the next step, which is called a covariant derivative, which I am skipping right at this moment, otherwise the video will be again too big. I have dealt it. So those who are interested in more knowing about Riemann geometry and how Riemann curvature tensor moves to the next variable, that is the covariant derivative, go to lesson number 11 and check it out. Finally, we come to what is known as the stress energy momentum tensor. And what is that? The stress energy momentum tensor is simple like this. Here it is the momentum density, this part. This is the momentum, this is the momentum density. This is the energy density, which is equivalent to the speed of light. So it will always be at the top. This is the shear stress, this is the stress, and this is the moment of flux. So what does it mean? It means this, that if I take the matrix, so from here I have just a second, this is equal to mc squared, that is why T00, the energy density will always be at the top. Why? Because it will always cease is the super speed of light, so it will not exceed. Now if I take this entire matrix in terms of T00 and those, and if I plot it here, it looks something like this. So first is the energy density, that is responsible for the space-time curvature. Pressure, I am crushing a sponge, and it is also causing a space-time curvature. This one is the energy flux. That means when a matter is moving along a place, there is a lot of energy, and that energy causes curvature. So first one is the energy which is causing curvature. Second is the pressure which is causing curvature. Third is the energy flux which is also causing the curvature. And one it is left is called momentum density. So energy and momentum, because they are closely related to each other, that is also plays a role in space-time. How can we put all those things together? We put it here. So energy, momentum, pressure and stress, all of them together is creating this kind of a dent, which is basically causing the curvature. So to summarize all involved, this is a geodesic, and I have shown it numerous times that if I take a path that is a tram and it is moving in a curved space-time, this will move in a curved space-time. So this is actually because of the present of the curvature, that is the presence of matter, and you see this is the source is the stress energy momentum tensor. So what happens? It is that the stress energy momentum tensor creates all kind of radiation, energy, momentum, density, flux, which causes the manifold to curve. And this curvature of the manifold is being measured by Ricci tensor, metric tensor, Riemannian curvature tensor, which we just learned, isn't it? And then it causes a bent. So we can say that an object moves through space-time in a straight line, but if the space-time is curved, this line will follow the curvature, obviously. And just like a sphere, and this curvature rises due to the effect that we call as gravity. So the left hand side, again you can go back to the video, and if you want to summarize and look into it, you're welcome. So you see the entire left hand side, the Ricci, the Riemann, the curvature tensor and the metric tensor, all are measuring the curvature. And who is responsible for the curvature? The stress, the energy, the momentum density, the momentum flux, and this is being measured by stress energy momentum tensor. So that brings us to the end of the beginner's introduction to Einstein's field equation. However, there are, I would like to summarize. So here is a summary. You can read. We learned the Einstein field equation, which measures the curvature, symmetry of the metric tensors, which defines the notion of curvature, Ricci tensor measuring how much the shape is deformed. Ricci tensor measures also the geodesic, positive, negative, zero. Metric tensor distance, volume, curvature, etc. Riemann curvature, that is the deviation in terms of parallel transport, relation between Ricci-Riemann and Riemann curvature tensor, and stress energy is responsible for the energy momentum tensor, which is a kind of a generalization of Newtonian mechanics which gives rise to gravity. Now there are two things which I have skipped, I mean to say due to lack of time, or the video is getting too long, which I will cover up in the next part of the video, which is basically called what is the curvature scalar and what is called the stress energy momentum tensor in a little bit more details. Thank you for very much for watching this video. Please subscribe to my channel Physics for Students. Click on the bell icon to get all the notification from Physics for Students. This is my contact ID. You can even subscribe to my channel General Relativity Expand, and you can follow me on my Instagram, Facebook, LinkedIn, and now at Twitter channel. I also have a fan page of Stephen Hawking where I keep on posting numerous posts related to education, physics, mathematics, biographies, discoveries, cosmology, and whatnot. So you can follow that at Facebook/Hawking Life and Works. Thank you very much for watching this video. Please put up your comments. What do you feel? How do you like? If you want to know more, you can contact me at my email ID. You can put up the comments, and I'm sincerely thankful for watching this video. Physics for Students will be soon back with yet more interesting videos, but till then, goodbye.